All right, we are recording now. Let me hit a couple of what just happened. There we go. I don't know what it's doing here. There we go. It finally came on. Several announcements. They're not really major. Well, some are. Let me start with tomorrow, okay? Normally my office hours on Tuesdays and Thursdays are 10 to 12 in the morning and 3:30 to 5:15 in the afternoon. However, tomorrow they have scheduled us for our, what they call, planning hearing, is what they call it, from 10 till 11 tomorrow morning on the Birmingham campus. Okay, now, I had hoped, I had put out the request for all the information and stuff, and had been compiling it and stuff, and as of Thursday, one instructor had not submitted, and he's pretty major because he runs a grant, and had not submitted any of the data from the grant, and that was going to be part of the, our student learning outcomes and that kind of stuff. So and he had decided to take last week off 4 days. So he wasn't in. So I did call him and catch him at home and ask him about it. And, I thought I'd said that to you. I said, well, I don't ever. He found the email from me and said, oh, no, I didn't answer this. I would have remembered that. So 2 months later, he said, I'll get you the data tomorrow, which is Friday. And so late Friday, he finally got it to me. So over the weekend, I was putting it together with the others. And but he said, when he sent me the data, he said, I'll have to give you the documentation, which is very important too. I'll have to give that to you next week. So that means that I have no time today. I was in class from 8 this morning. I'll be here till 9 o'clock tonight. I just had a 20-minute break. I will have one more 20-minute break at the end of this class, and then 2 10-minute breaks in my physics classes to set up labs. And that's all the time I've got off today. And here's Jasmine. Okay. So what that means is I've got to go to the Birmingham campus first thing in the morning, get the documentation, put it all in the notebook, and get everything ready for the hearing. So not only will I not have office hours from 10 till 12, I won't even be on campus tomorrow morning at all. I'll go straight to the Birmingham campus, we'll have the hearing, I'll come back over here and hopefully get here before my 12 o'clock class. Then the 12 o'clock class meets from 12 to 3:30, and then I'll be in the office from 3:30 until 5:15. But with that, I also know of at least one student who's coming by to do a talk about a research project. So that's going to eat a chunk of time tomorrow afternoon. So if you got to see me, come on by. I'll work around that student. Okay. So that's tomorrow. The rest of the week is pretty whatever normal is now. For the rest, should be office hours as normal. Reminder, next month we have class today, we have class Wednesday, we have class on Monday. I'll give you your final exam to take home on Monday. Oh, I think I recognize you from somewhere. Where is that?
Don't get too familiar though, it's time to go back to work. Sorry. But I do have presents.
Okay.
So,
Do you want your second test?
Yes.
Okay. You already have your second test, right? Yeah. What's that? I'll be passing out the final on Monday.
Fantastic. I will have this back to you by Wednesday.
Okay.
And I also plan to turn in my report to you then.
Okay.
So.
2-4. There's test 1. Oh, no wonder I'm in the wrong class. Okay, there's test 1. Test 1. Test 1. Test 1. Here's test 2. Do either of you have your test 2s available? Let me make sure I have, oh, here, I think I got it. That's test 1. Oh, yeah, that's yours. Test 2. No, that's not it. Okay. Right. Yeah, this thing, there, okay. Says evaluate the intervals, right? Okay. There it is. Okay. Unfortunately, it's not stable. 10 questions. The second page is calculate TN and SM. Last question. Right. Okay. Number 5, evaluate the integral dx over integral from 4 to 6. Yeah. Okay. Yeah, that's it.
Fantastic. Thank you so much.
All
I'm
right.
sorry again. But
Okay.
if it makes y'all feel any better, y'all do sound fantastic, and I am here in spirit. So
Okay.
I mean, watching
So,
at home. So,
okay. All right. Good deal.
thanks again.
Okay. Okay. Sorry, I marked this. So, he just mentioned the paper, and this, my second largest calculus class this term, with a whopping 7 or 8 students in it. I've gotten one paper in. Yes. So thank you very much for doing that. I do need your papers. And guess what? You only have 1 weekend left. Now, I'd rather not have them all come in on Monday, but if they come in, that's fine. But anything after Monday, you'll be losing points. So you actually get a bonus point if you get it in this week, and you don't get a bonus point if you turn it in Monday, and you lose points if you turn it in Tuesday or later. So down to the nitty gritty here. Okay. And then, as you just seen, a couple people have turned in tests today, so if you still have that second test out. Oh, which leads me to, I can now return your first test because I just got the last first test in. So why didn't I do this when I was back here? Okay, Chris is not here, Khalil's not here, Kayla's not here, Peyton is, Colton's not, Stuart, and Jasmine is.
Feels like everything comes together right at the very end. Still,
If it doesn't fall apart. Okay. All right. Now, I think I'll wait. There is one other announcement that has nothing to do with math that I do want to make, but I'm going to hope some more people will come in before I make that announcement. So let's just, yeah. Yes. Usually 3 significant digits is fine. You know, decimal points just depends on how many you got in front, but usually 3 significant digits is fine. I don't need a whole string because most of the time they're not significant. So. Well, I don't think I counted off of that unless it was the wrong whole number. All right. Now, I do try to give as much partial credit as I can. You know, the more work I can see, usually the more I can give partial credit. So keep that in mind. And let's see. So, the last test I will give you Monday. Okay, that'll be your final exam. It'll cover what we covered so far in Chapter 8. We should finish all we're going to do in 8 today and move on to, we're skipping 9, move on to 10. Should get a fair amount covered there. And next time finish up 10 and get into 11. And Monday we may get a little bit into 12. But the test will cover 8. We're only doing 3 sections in 8, 2 in 10, and 2 in 11. And then we may get a little bit into 12. If we do, that'll be on your final 2. Okay, again, get your papers in to me as soon as possible and get your other tests in as soon as possible, and I'll be giving your final test out to you at the end of class on Monday. And then I will need that back as soon as you can get it to me, but that could be Tuesday, Wednesday. Technically, it's not due till Wednesday. I'll accept it on Thursday, but please try to get it to me no later than noon on Thursday, if at all possible, because that will be into August, and we go off our 4-day work week in August. However, I have an infusion on that Friday, and I will be out on, for that whole day. So I won't be able to take it on Friday, and we're leaving town on Saturday. So I've got to have your last test and everything you're going to turn in by. I'd rather have it by noon on Thursday, but get it to me by Thursday. What's that? Yeah, next Thursday. Yeah. I'll give you your final next Monday and get it back to me by Thursday. And the final is not comprehensive. It's just what the last section we're covering. Chapters 8, 10, and 11. And maybe a little in 12. We'll see how we go. Now, the one other thing, and this does not have to do with math. I was going to wait till more people came, so I'll probably say it again. I take it that both of you are residents of Alabama, right? And I take it that you're probably both 18 years old or older. And I sure hope that you're registered to vote. Yes? Good. Okay. You know there's a primary vote coming up for the Senate seat. Yes, exactly. The 15th of August. And the reason I'm saying what I'm saying is, if you weren't registered yet, Monday is the deadline for that, to be able to register in that. Now, do any of you live in the city of Birmingham?
I do, but I'm registered to vote
In Auburn, okay. Well, wherever you're registered. Now, if you're registered down there, are you going to be there on that? Okay, check about getting an absentee ballot. Okay, please vote, folks. That's the bottom line. Please vote. It just angers me when I see someone winning by 50 vote margin and 35% of the voters have voted. I mean, you got 17% of the people decided who's representing us.
Not exactly very turnout in previous elections here, but we haven't had to have a brand new senator in a long time.
Right. Well, nevertheless, vote every time the polls are open. Vote early and often. No, I mean, but yeah, please vote. In my mind, so I say, it gives you the right to gripe. Because if you haven't voted, don't complain. Because you had a shot to have your voice, you didn't take it. You don't have the right to gripe unless you vote. I like to gripe, so please vote. All right. Too much of that maybe, but all right. Picking up where we left off last time, we're in Chapter 8, Further Applications of Integral and Taylor Polynomials. We won't get to Taylor Polynomials. I hope to do a slideshow on them. I don't think I'll do that. You got your books, look it over. I don't think anyone really requires you to have that. They are really powerful things. When you have a calculator and put in sine of 0.3, that's not looking up in a table what sine of 0.3 is. It's doing a Taylor series and calculating it. Taylor series converge really quickly. They're really powerful things. I wish we had time for them. We don't. So it's worth a look. I don't think you'll probably ever need it, but if you do, you know where to go to find it. Okay, we're in section 8.3, which is the last section we'll do in this chapter. It's a very short chapter, but we're only doing 3 of the 4 sections. So we were going to talk about symmetry, and this is an example. What if you had a lamina, they call it, a symmetric plate, uniform density, all that kind of stuff that we've been doing on all of them. But it's symmetric about something. This happens to be symmetric about the y-axis. Guess what? If everything's even, everything's symmetric, you know, uniform density, all that kind of stuff, you know the x component of the center of mass is going to be right there on the y-axis. If everything on the right is the same as on the left, everything is, you know you've got to be. So you don't have to calculate x bar or x center of mass. You don't have to. You can look at the problem, if it's symmetric, uniform density, and say it's got to be there. Okay? Now, that leads to the symmetry principle, okay, which is basically what I was just saying, but given as a theorem now, is this. If a lamina, meaning a uniform plate, uniform density plate, is symmetric with respect to a line, any line, even a diagonal line, you know that the center of mass lies on that line, wherever that line is. If the lamina is symmetric with respect to any line, the centroid lies on that line. Okay? So that can take close to half of your work away if you let it. Okay? Let it. All right. I guess we'll just go on and go from here. Find the centroid of a circular half disk of radius 3. Okay? So here's your picture. Circular half disk. You get to draw it anywhere you want to. Draw it centered on this origin. Plus 3 to minus 3. There's your half disk. Radius 3. Now, if that was a whole disk, it would be its origin. You don't have to do either one of them because it's symmetric about x and y. But this one's only a half disk, so you know it's symmetric about the y-axis. So therefore, the x component of the center of mass is 0. You've done it. You don't have to do a thing else with it. Okay. Now they give this semicircle as y is equal to square root of 9 minus x squared. And sure enough, that's right, because if you squared both sides, that would give you y squared is equal to 9 minus x squared. Add x squared to both sides. X squared plus y squared is equal to 9. That's the equation for a circle. A full circle, this being the positive square root, means you've got the top half of the circle. So there's your y in terms of x. Okay? You already know the x component of the center of mass is 0. Okay? So all you're looking for is the y component of the center of mass. Okay? Now, how do you want to do that? Frankly, it looks like to me, if you're looking for the y component of the center of mass, it looks like to me, if you did your, unfortunately, dx's. Now, the reason I want to do dx is you've already got y as a function of x. Now, it's really easy to get x as a function, well, sort of easy to do x as a function of y, but it's really, if let that be your dx, your center of mass with respect to y is going to be halfway that, okay? So we're using sort of the alternate formula that we had before. So, that's what we're dealing with. So let's do our, now that would be your x m sub x. I was trying to remember the moment with respect to the x-axis. That's the y component of your center of mass will come out of this, is going to be the integral, well, let me not write the integral sign too soon because we're probably going to have some things out front. May not, but okay. Let's just give me a little more room here. Okay. I don't think I'll need that much, but okay. Now what is that component? Okay. It's the distance from the x-axis, right? And that would be the midpoint of that segment there, that line. So the midpoint there would be the top, which is the square root of 9 minus x squared minus a plus 0, and then take half of it. So there's the midpoint, okay? So I know I can take out a 1/2 here, okay? The area of that thing is the height of it, which would be the square root of 9 minus x squared times dx, okay? So if you go back to that, the 1/2 we pulled out is from the other, and then you have this thing times that. Well, it's just your function squared, and when you square the square root of 9 minus x squared, you just get 9 minus x squared dx. Okay, that's going to give your m sub x. Everybody agreed? How do you do that? Oh, and where did your x going from? Oh, wait a minute. It looks like everything's symmetric this way. So rather than going from -3 to 3, let's just go from 0 to 3 and double it. So that'll wipe out your 1/2. I'll buy that. Okay, so there's your integral. What does that give you? Antiderivative of 9. Antiderivative of 9x minus 2 cubed over 3. Evaluate that from 0 to 3. I can do the 0 part, so I'll take care of that. If you'll do the 3 part. 27 minus 9. Okay, so that's equal to 18. Okay, there's your m sub x. Now what we need is the m. Okay, well the m is pretty easy too. That's the integral. And again, we're going to double. So 0 to 2 of the square root of 9 minus x squared dx. It was just that last part here. That was your area part, the length times the width, okay? So, that's a little bit tougher integral to do, okay? How would you approach that? Second? No, I wish it could, but I don't see any way to do integration by parts. You would need a u and a dv, and the only dv you'd have would be a dx, and that's not going to get you there. What's that?
Where is this part coming from?
Oh, okay. This is the mass of it, and the density we're assuming is 1. So you're doing the height of this, which is square root of 9 minus x squared times the thickness, integrating that -3 to 3, but because it's uniform, we're doing twice 0 to 3. It's just this thing right here. Right? Length times width.
Where is 0 to 2?
What's that?
From 0 to 2.
Oh, it's not a 2, that's a 3.
Oh, okay.
I'm sorry, it's a really ugly 3. Okay. Yeah, it was, I picked up the pen too soon and it just left it hanging there. Now, if I said 2, it's because there's 2 out front and I just got them crossed up, but that's supposed to be a 3, just like the one above. Okay, this form here.
I remember that
It's a trig substitution.
Oh, okay.
right. And what I would say for that one is I usually like to use Greek, lowercase Greek for angles, so let theta equal 9 minus x squared. No, sorry. Doing it the wrong way. This is going to be a sine, so let x equal 3 sine theta. Okay? That 9, the square root of that gives you what the coefficient is. Okay, if you do that, then next step, dx is equal to 3 derivative of sine, cosine theta. All right, we have some other things to do. I'll write them all out here. X squared would be 9 sine squared theta, right? Okay. And 9 minus x squared would be 9 minus 9 sine squared theta, right? Okay, factor out a 9. 9 times 1 minus sine squared theta, right? And let's see, what is 1 minus sine squared theta? Good old Pythagorean identity. Oh, it's the one we use so much. Sine squared theta plus cosine squared theta is equal to 1. Always, always, always. Okay? So therefore, subtract a sine squared from both sides. And you get cosine squared theta is equal to 1 minus sine squared theta. So this will be 9 times cosine squared theta. Right? Now, let's go back and plug in. Well, let's do this. That was 9 minus x squared is 9 cosine theta squared theta. Take a square root of that, and the square root of that would be, square root of 9 is 3. Square root of cosine squared would be cosine theta. Okay, so that's what we're integrating. So let's bring this over here. Okay, and that would be 2 times the integral. Now, if we're changing our x's to thetas, we need to change our limits as well. So when x equals 0, what would theta have to be? If x equals 3 sine theta, what would, if x is 0, theta would have to be 0 too, because sine of 0 is 0. So the theta would be going from 0, and if it's going to 3, if x is equal to 3, that means sine theta would equal 1, so what would theta have to be? Where is sine theta equal to 1? Pi halves. Okay? I'm not going to tell you a trick, teacher. You're so. Okay, never mind. Okay. All right. So 2 times that, and the square root of 9 minus x squared is 3 cosine theta. So let's pull that 3 out and combine it with the 2 and make that a 6 out front. Okay. And that would just be a cosine theta. Oh, but our d theta, our dx, is another 3. So 3 times 6 would be 18. So this 6 now becomes an 18. And we had a cosine theta from there, and this gives us another cosine. So cosine, ooh, yuck, cosine squared theta. And my board just gave way on me, so I have a really ugly mark there. Okay. 3 times cosine squared theta without the O. Let me get the O back in there. D theta. All right, that's what we're integrating. Now, we could make you go through and see if you can recreate what cosine squared is, but I know that one's in the back of the book. So let's just turn to the back of the book. Under trigonometric forms of integrals, number 35 is cosine, the integral of cosine squared u du is 1/2 u. So this will be 18 times 1/2 u, and our u here is theta, 1/2 theta, plus 1/4 sine 2 theta. Okay? And then you have a plus c, but we don't need a plus c because we're have a definite integral. All right, first thing I'm going to do is take out a 1/2 from both of those and make this a 9, just to make it easier. So that's going to be a 9 out front, times, and this is evaluated from 0 to pi halves, so that'll be pi halves, theta equal pi halves, plus 1/2, there we still have another, goodness gracious, okay, sine of 2 theta. Well, if theta is pi halves, 2 theta would be 2 pi, right? Okay. Well, what is sine of pi? Zero. Cosine.
Oh, yes, cosine of pi.
Well, cosine of pi is -1. Yeah. Okay, so this will just be, that part will be 0. So basically, we have 9/2 pi, which is rather bizarre, but we can do it. So what you have then, your y bar is your m sub x, which was 18, divided by 9 pi over 2, that's your m. The 9 will go into 18 twice, and you flip over this, that would be 2 divided by pi halves, which is the same as 2 times 2 over pi, that would be 4 over pi. And 4 over pi is exactly what they got there. Let me erase this line so you can see it, and there it is. 0 we got by inspection, and 4 over pi we got from doing that. Okay. Okay. See how and why that was done? Okay. So let's step back just for a moment. Just looking at it, it's a lamina, it's uniform density, symmetric, everything's fine. So you know the x component center of mass is going to be 0. X equals 0, there it is. Now the y component, that's what we're doing, so we do the m sub x, how far the moment with respect to the x-axis. And because this is just set up so nicely to do it to dx here, so let's just leave our y to be that. So what we have to get the center of mass of this little strip here is just going to be halfway up the strip, which would be 1/2 of the y value. So that's where that first 1/2 came from. Okay? That's what this was. Maybe 1/2 of that y value. Times the area of that strip. Well, the area of the strip was the y value again, which is this, times the thickness of it, which is dx. So you have this over 2, that's why the 1/2 was out front. 9 minus the square root of 9 minus x squared times the square root of 9 minus x squared, which is just 9 minus x squared dx, integrated from the -3 to 3. But wait a minute. That's perfectly symmetric there, so why not just go 0 to 3 and double it? Doubling it took out your 1/2 here, so that first part was pretty easy to do. You did the integral 9x minus this, you plugged it in. That gave you 18. That was the moment with respect to the x-axis. Now, the denominator is just the total mass of this. And again, we're assuming the density is 1. I haven't said that. I think I said it, but I didn't write it down, because with lamina you can assume that. Because you have a density in the numerator, density in the denominator to go out, so who cares what the density is? So we can just assume it's 1. Okay? But now the total mass is the integral of this thing here, length times width, from -3 to 3. Since it's uniform, we can do twice that from 0 to 3, so that's where this came from. Total mass is twice the integral from 0 to 3, square root of 9 minus x squared dx. Now, the bad news of that was, you can't integrate that form, but it does set up very nicely for a trig substitution, which is x equal 3 sine theta. And the reason that works so nicely is when you plug that in, this will be 9 minus 3 squared times sine squared theta, so that would be 9 sine squared theta. Factor out the 9, which we did here, and that gives you 1 minus sine squared theta, which is cosine squared theta. Now that's the product of two perfect squares. Square root of minus 3, square root of cosine squared of cosine. Okay? So that gave you this part. Okay? Then we have to do the dx. If x is 3 sine theta, dx is 3 cosine theta. So when you plug in that for your integrand, 3 cosine theta, and then you have another 3 cosine theta for your dx, that would be 3 times 3 is 9, times 2 is 18, so that's where the 18 came from, right over there. And all you've got left in here is the dx was this, and the square root of that was that. So we already pulled out the 9, so you have cosine squared. That was the integral we went to the back of the book and found was 1/2 theta plus 1/4 sine 2 theta. So if you're going from 0 to pi halves, sine of 2 times pi halves would be pi, and that's 0 minus this one. Theta is equal to 0, sine of 0 is 0. So that part doesn't contribute a thing to you. You just have the pi halves here. So it's 9 times pi halves, so it's 9 pi over 2. There it is, 9 times pi halves, 9 pi over 2. Well, then your y bar would be your m sub x, which we got to be 18, divided by the 9 pi over 2, which was your mass. And the 9 will go to 18 twice. You got 2 divided by pi over 2, which is the same as 2 times 2 over pi, so that is 4. That is as the y component of the center, that's the y bar. Is that? Okay. Does that make sense? All right. Now, here's a fun little one. We're going to use additivity and symmetry. Find the centroid of the region R in figure 17. It's 14 on the slide set. I'll blow this up for right now. I'll have to reduce it pretty soon to write. I feel a headache coming on. I don't know why. My head's been stopped up this morning, so that may be it. I don't know. But it's hard to breathe. Okay. It says, find the centroid of the region R, shown here. It's that centroid that connotes to you that this is a lamina, okay, uniform density. So we have that density be 1. That's the first thing they say. Doesn't matter what it is because you're going to multiply and divide by it, so it goes away anyway. Now, they talk about the additivity of moments, and they certainly work, but then the so we can just do each one of them separately and then combine them together. Okay. Now, before we go anywhere else, what's your x component of the centroid? 0. X equals 0. It's got to be, because this is symmetric, that's symmetric, everything's symmetric. It's got to be on that line, and on that line x is 0. Now, second point is where, okay, let's just set up this figure a little bit. They're telling us that this point right here is y is equal to 3. Now, when I first glanced at this, I thought this is an equilateral triangle and a circle. This is not an equilateral triangle. How do we know that? Because this leg, this base down here is magnitude 4, and this one up here can't be magnitude 4. This one over here can't be magnitude 4. This is 3 from bottom to top. Okay? And there's no way that could be 4. But we can fairly easily come up with one of these lines here. So a pretty easy thing to come up with. First, what's the slope of that line? The one right here. It intersects at 0, 3, and 2, 0. You got 2 points. You can calculate the slope. 3 minus 0 over 0 minus 2. So that's minus 3 halves. There's the slope downward. Y-intercept is at 3. So y is equal to m, which is minus 3 halves, x plus 3. Okay? So there is the equation for that line. Now, I should have, before I did that, do we know the centroid of the circle? Circle is a uniform plate, uniform in every way whatsoever. Not only do you know the x-coordinate must be on the y-axis, but the y-coordinate of that circle has to be, and as you see here, this is a circle of radius 2, so that means that that point there is 0, 5, and that is the centroid of the circle. Now, the centroid of the circle is not the same as the centroid of the whole thing here, so we're going to have to play around with that a little bit. But we can knock that out. All we have to find now is the centroid of this, and we know where it is. It's on the y-axis, so we know its x component is 0. Okay? So what we've got to do now is figure out where on this line its center is, and then get them to reconcile with each other, the two centers. Okay. So, like I said, we do know that this line here is, oh, I can't write on that until I reduce it. Y is equal to minus 3 halves x plus 3. And y is equal to mx plus b. slope here is minus 3 over 2 x, and y-intercept is 0, 3. So there's that. Now, because this is symmetric, all we have to do is find the y component of the center of mass here, and that'll be the same as the y component of the center of mass of this triangle would be the same as for that triangle. Okay? X component we know is 0. Okay? So the y component, if we can find it for this one, we know that'll also be true for that, because those are exactly symmetric. So let's see if we can do that. And since you're looking for y component, oh, it's just as easy to keep it like this. Let's do a little section of this. It's the height of that is this thing, and the width of it is dx. Okay? So, and how high it is from that, that's the midpoint. Okay? Okay. So it would be the height divided by 2 times the height times the width. Okay? So this your moment with respect to the x-axis of the triangle would be the integral. I always try to leave room just in case I need to write anything later. Goodness, I'm having a hard time breathing. All right. You got a 1/2 out front because you got, you're doing the midpoint there. But you're going to double this, so that'll wipe out the 1/2. You're doing from 0 to 2 because you're only doing one side of it, and that would be your y value the y value times 1/2 the y value. We got the 1/2 out front. We already wiped it out with the 2 for the symmetry issue. So basically this will be this thing squared. This will be a minus 3/2 x plus 3 squared. Okay, I can't get that. This is so ugly. I was trying to get the 3 to look like a 3, and the more I mess with it, the worse it got. Okay, that's it. So, the first part of this, the midpoint there is 1/2 that function. The length of that is that function times the width of that is dx. So that's the only part I have it written in here, and that will be the moment with respect to the x-axis of the triangle. Okay, so let's go on and multiply that out. That would be 0 to 2 of when you square a binomial, you square the first term, which would be 9/4 x squared minus 18. I'm sorry. Yeah. Okay. My pen just quit writing, so I had to go back. Let me clean that up a little bit. It's twice the product of the two. Okay. It's the square of the first, twice the product of the two. That gives you your minus. It's 2 times 3 halves times 3. Well, 2 times 3 halves is 3. Times 3 would be 9x, and then plus 9. Okay? And that's then multiplied by your dx. Okay. Well, 2 times 9/4 is, I'm sorry. Yeah, 2 times 9/4 is 9 halves. X, see what we're doing there? Twice the exponent times the coefficient. Drop that by 1. Minus 9. Let's see, I've got another term that I need to get in there. Let me back up. I really need to go clear my head because I'm having trouble breathing. That's not what I wanted. Okay, that. Okay, let me put this on pause. I hate to do it so. Okay. As soon as we get the projector back on, here it's coming. So let's just review your moment with respect to the x-axis is the midpoint, and we're just in the triangle here. And the line here is y is equal to minus 3x plus 3. Now the only, just happen to think of this. Yeah. I think that would still be okay. Yeah, we're just integrating that, this part. The height, half the midpoint is that divided by 2, which that was the 1/2 that's out front. Then the area would be the height, which is again that, times dx, okay? And then we're going to double that, and that's got rid of our 1/2 and goes from 0 to 2. So yeah, that should be legal and everything. So when we squared the that function, that linear part there, that gave you 9/4 x squared minus twice that would be 9x plus 9. Yeah. So when you do the here I go, can't talk again. Integrating that, this is going to be an x cubed over 3, but the 3 will cancel into the 9 3 times, so that would be 3/4 x cubed. Do you see that? This is what I was trying to get my eyes to focus on before, and I was just having such difficulty. And this part would be minus 9/2 x squared plus 9x. Evaluate that from 0 to 2. Okay. All right. 2 cubed is 8. 8 divided by 4 is 2, and 2 times 3 is 6. I sure hope that part's right. Minus 2 squared is 4. 4 divided by 2 is 2. 2 times 9 is 18. Plus 18. 9 times 2. And sure enough, those go to 0. So that leaves you your m sub x was 6. Now we do the mass. which is very similar to this, okay? It's going to be twice the integral from 0 to 2, just like we did before. But now we only need one of those. We don't need the 1/2, and we don't need the second one of these. It's just a minus 3/2 x plus 3 dx. That's the only part we need for the mass part. The length times the width. Dx is the width from 0 to 2 and double it. Okay? And what does that give us? 2 times antiderivative of negative 3/2 x. Negative 3/4 x squared. Perfect. Plus, second, 3x. Evaluate that from 0 to 2. Okay. The 2 squared is 4. And that'll wipe out your denominator. That's minus 3 times 2 would be a minus 6 plus 6 times 2 is 12. So that would be 6. Now, if I did all that right, that comes up, but my center of mass is just 1. The y bar is just 1, because it would be this one over that one. Okay, 6 over 6 is 1. Let me just take a look and see. Okay. Now, I want to time out for a moment here. I got a little carried away there. Remember, we're doing this by symmetry. That gives us the the x component, 0. But the moments add, not the center of masses add, okay? So basically what we needed to do was do the moment for the circle and add it to the moment we just calculated for the triangle. So I didn't need to go back and do this y bar because we don't need that yet. So let me take this out of there. That y bar for the triangle, that was true, but it's not useful in this case. So this is mx for the triangle. Okay, now, what I said, which is perfectly correct, the center of mass for the circle is 5, 0, 5. Hey.
How are you doing?
Good, thanks.
I just wanted to ask you a quick question. I have been trying to get in touch with you. I need to sit down with you and go over to see, maybe for you to advise me. Do you have a time slot?
Well, not today. I've been in class since 8 o'clock this morning, and I won't be through until 9 o'clock this evening.
Is there anybody else I can see?
Any of the instructors on the hall will be fine. If you need to see someone today, then see one of them. Tomorrow, I've got to be on the Birmingham campus in the morning, but I'll be back on this campus for a 12 o'clock class that gets through at 3:30. I've got a lab with it.
Okay.
And so between 3:30 and 5:15.
See, I work Monday through Friday, so it's hard for me to get by here. I was off today.
Yeah.
So when you say anybody on this call,
Okay. Let me pause this for a
I don't
moment.
mean to interrupt.
Yeah. Well, let me. And again, it's the moments that add, not the centers of mass that add. We got the moment for the triangle. That's this one, 6. How do we get the moment for this? we know the center of mass. That's obvious. It's 0, 5. Okay? For that circle. It's got to be. Well, if you know the center of mass, okay, let's think about that. The center of mass, let's say y bar for the circle, is equal m sub x, and by the way, this y bar is 5. Yeah. Okay. That's your m sub x divided by m. Now that's m sub x for the circle divided by m for the circle. This is m for the triangle down here. Don't get those crossed up. Okay, and this is m sub x for the triangle here. Well, we know what the mass of the circle is, don't we? Do we? Mass of the circle? Do we know the mass of the circle? Do you know the area of a circle? That is exactly pi r squared. What's the radius of that circle? No, the center is at 5, but the radius goes from 5 to 3 or 5 to 7. So what's that? 2. So the radius is 2. So pi times 2 squared, that would be 4 pi, right? So the mass of the circle, since the density is 1, that would be 4 pi, right? That's what we just said. Okay, well, the moment with respect to x of the circle divided by 4 pi has the equal to y bar, which is 5. We already knew that. So that implies that m, the moment with respect to x of the circle, is 20 pi. Multiplied 4 pi times 5. Okay? 20 pi. Pi didn't write. Okay, there it goes. 20 pi. 5 is equal to mxc over 4 pi. Multiply both sides by 4 pi. mxc would have to be 20 pi. Okay? mxt, we just found to be 6. So the moments add. So the moment total with respect to the y-axis, no, let's not put total, just put y, m sub y, would be 20 pi plus 6. Okay? Now, the mass of the triangle we just determined was 6. The mass of the circle we just determined was 4 pi. So the total mass, okay, is equal to 4 pi plus 6. Okay? So your y bar is equal to the total mass, m sub x, total, which is, I put m sub y, this is m sub x. Something didn't sound right there. Okay. That's mx for the triangle, mx for the circle, and that gave you your total mx. So your y bar would be 20 pi plus 6 over 4 pi plus 6. Okay? Which would be, you can factor out a 2 in the numerator and a 2 in the denominator. That would be 10 pi plus 3 over 2 pi plus 3. Okay? Not that that is anything better. And if you did that, they left it as 6 plus 20 pi over 6 plus 4 pi, which is exactly what we got. They actually multiplied that out and added and got about 3.71. which would be somewhere right about there. Okay? Because right here would be 4, and this is a little bit closer to 4 than it is 3. So your center of mass here was at 1. Center of mass here was there. So yeah, that looks fairly close. There's more mass of the circle than there is of the triangle, so it does tend to pull it up a little bit. So there's your center of mass. That was a rather bizarre type thing. Remember, it's the moments to add, not the center of masses to add. Okay. I'm trying to figure out what the figure 18 is there for in your text. And I do not see anything that refers to figure 18. Perfectly good figure, but I guess, I mean, oh, here it is, under step 3, the moment of a triangle. That is not the same triangle we have here, so I'm trying to figure out why they did it that way. Boy, that seems like a hard way to do it, but they did it that way. It's fine. I think the way I did it was a little bit easier than that. All right, any questions on that one? That was example 5, a fairly involved example. Okay. Oh, here's that part of the figure. I may have to reduce this, and it seems like a really awkward way to work this problem, because number one, that's not the triangle we have that we're messing with. But what they're saying is for any triangles, okay, you can use this form. If this length is what you're looking for here, your similar triangles say that if your original triangle is 1/2 b times h, which h is the total height here, that's the area of that triangle, 1/2 b times h. Then you're looking for the length of this triangle. Then this y, how high you are above the x-axis, you might say down here, the base down here, that would be your y. The height of this triangle would be h minus y. The length is y, so L of y. L of y over h minus y is the same ratio as b over h. Okay? And then you can come up with an expression for L of y and then go from there. Our triangle is so much easier than this. Why would they have you do this? Well, this would be for any generic triangle. Okay? So leave that alone for now. I think the way we did it was better. All right, now here's something else. Archimedes' law of the lever. I do not see that. Oh, that's next. Okay, we're going to come back to that. No, we're not going to come back to that. For some reason, they do not have the theorem of Pappus in here. So, neither of you have books today? It's what? Okay, well, I'll write this in then. This is theorem 2 for this section, the theorem of Pappus. Let R be a region nice name to call a region, R, in a plane, in the plane of area A. Now it's a R be a region in the plane, but R's area of area A. Okay, that doesn't mean the plane has an area of A. This R's region area is is area A, okay? That we rotate about an axis that is disjoint from R. Okay, now what do we mean disjoint from R? Let's just imagine, this isn't what this is doing, but let's just imagine, hey, oh, you like yourself out? Yeah, I did. Let's just imagine that here is the y-axis over here. Okay, ignore the little mass here. Here's the y-axis here. Let's just say, well, let's just use this is the center. This will be your origin. What you're going to do is rotate this circle around that axis. And when they say it's disjoint, nothing on this circle can touch that axis. Okay, this would be obvious. Okay, if you're rotating this triangle around this axis, that would be fine. But if you're rotating something like here, and part of the circle actually intersects the axis, that's not disjoint. Disjoint means there's nothing in common. Okay? So you,
CAD drawings, if you're involved in drawing,
right.
it cannot intersect itself with the
Exactly.
program.
That's the point. That's the point. And so you can revolve this around there, that around there, but you couldn't revolve something that included the axis. Yeah, you can't include itself there. Disjoint, it means their intersection is a null set. Okay, that's what disjoint technically means.
Drawing types in CAD really difficult to calculate how far the bends are first, and oftentimes it doesn't work.
Right, yeah, because you could have pretty serious design problem then. Okay, it's disjoint from R. Then the volume of the resulting solid, we're going to take that and revolve it around whatever your axis is, a disjoint axis, revolve it around there, then the volume of the resulting solid okay, the volume of that solid is the product of the area A with the distance traveled around the centroid, by the centroid of R. Product of A times the distance traveled by the centroid. This is one of the reasons we use that. Of the region R, okay? And they keep interchanging A's and R's. A is the area, R is the region. So basically what we're saying is, if this were going to revolve around this axis here, like this, what you get is a big donut. Well, not a very big donut, sort of skinny donut with a big hole in the middle, okay? And the total volume of that would be the area here times the distance the centroid moved. Well, the centroid, if that was a perfect circle with lamina, that kind of stuff, that would just be that distance there. In this thing, that would be, let's just call that L or R. I don't want to use R, I will use that for the region. But let's just call it L. So pi L squared times the area of that. That would be the volume of the region. Okay? Attributed to Pappus of Alexandria, mathematician, the 4th century BC. Now that was around the same time, I believe, as Archimedes that we're going to look at. He's actually, Pappus preceded Archimedes. Okay? And Archimedes came up with the law of the levers, which we're going to do next. But let's just do quickly example 6, which uses this one. Find the formula for the volume of a solid torus obtained by rotating a disk of radius A. So we'll call this a disk of radius A. Centered at B0. So we're going to call this B. Okay. B0, 0 on Y. About the y-axis where A is less than B. Yeah, way less than B, as shown in the figure. Their figure's a little different from ours, but you got it. Rotating that around the y-axis, and we want to come up with the volume. Well, what's the centroid of that disk? Okay. Pretty obvious that the centroid here has to be B0. Okay, so the centroid, I'm going to call it center of mass, it's the same as centroid, that's going to be B comma 0. Okay? Now, theorem of Pappus says then that the volume is equal to the area of that, and that area, well, we'll get to that in a minute, times the distance it moves. That would be 2 pi times B. Okay? Well, what's the area? The area is pi r squared times 2 pi b, and that would be 2 pi squared this is A here, okay, 2 pi squared A squared B. Okay? 2 pi squared A squared B. Got it. All right. That's the theorem of Pappus. Okay? Now, let's clear that. And let's take a look at Archimedes here. And they don't have any example of this. They just show it. But this is... it's very, sorry, very much an application of the center of mass. Okay? Archimedes' law of the lever. Okay? Mass 1 times the length it is from the center is equal to mass 2 times the length it is from the center. That's if this is balanced. Okay, and if it is, then you're hunky dory. This would indicate M2 is a good deal larger than M1 because by the picture L2 is a great deal shorter than L1, but they will differ by the same ratio. Ratio of L1 to L2 must be exactly equal to the ratio of M2 to M1. It's just the inverse relationship. And that's Archimedes' law of the lever. Now, if you did want to write on Archimedes, and he's a fascinating character, here's a historical perspective on him, but you can't use this as your paper source. You can use this to look into and find the paper source. Okay. All right. Do you want to do the preliminary questions?
Sure.
Okay, let's do those. The summary there just summarizes all that we've done so far. So let's look at preliminary questions. I don't think, we have any more slides. What are the x and y moments of a lamina whose center of mass is located at the origin? The x and y moments of a lamina whose center of mass is located at the origin. Well, no, it doesn't say what the shape is. It says what are the x and y moments of a lamina whose center of mass is located at the origin. If the center of mass is at the origin, that means x bar is equal to 0, and y bar is equal to 0, and x bar is m sub y over m, and this is m sub x over m, and if that's 0, that means These two have to be 0 because the mass is not, of course, but it didn't matter if it was or not. You can't divide by 0, so obviously the moments would be 0. Okay, that was just a sort of a conceptual thing. And we'll make sure that they got it right in the back. Sorry, I can't. 8.3, preliminary question. Mx, My is equal to 0, right? Number 2, a thin plate has a mass of 3. Okay, let's just call this is 3. Okay, use their picture. Thin plate has a mass of 3. What is the x moment of the plate if its center of mass has coordinates 2, 7? So x bar is equal to 2, y bar is equal to 7. Okay? A thin plate has a mass of 3. All right. Well, what they're asking for is x moment. What is the x moment related to? X bar or y bar?
That'd be X bar.
Second?
X bar.
No, that's the backward part. Yeah, the moment with respect to x is related to y bar. The moment with respect to y, because the mass times the distance from x is
right. You're using the other. Yeah.
right. So what they're asking about is x bar. M sub x, the moment. So we're going to use the y. This is m sub x over m. But they told us what the mass was, 3. So therefore m sub x is equal to 3 times 7, which is 21. Okay, so that had better be 21. M sub x is 21. Good for them. All right, number 3. The center of mass of a lamina of total mass 5 has coordinates 2, 1. What are the lamina's xy moments? Well, it's almost the same as what we did. This was 1, this was 2, this was 3. Okay? Center of mass of a lamina has a total mass. It's a weird way to express it. Anywhere m is equal to 5. Total mass. The center of mass has coordinates. So x bar is equal to 2. Y bar is equal to 1. So what are the lamina's x and y moments? What is, let me change something here. Yuck! Okay. Two ones. Okay. Goodness gracious, my head. So, how is x bar related to either the x or y moment?
Just forgot.
There it is. Y bar is equal to?
Oh, yeah. So the mass. So it would just be
M sub x over m.
Right. So it would just be.
And the m was 5.
Yeah.
So this would tell you m of x, moment with respect to x-axis is?
2.
No.
Bar. So it's just.
if 1 is equal to mx over 5,
Uh-huh.
what is mx? Multiply both sides by 5.
Oh, it must be
5, exactly. Okay?
I think in 1/5, because normally you multiply, you solve the equation by multiply or divide.
Okay? So what would be your m sub y?
So 7y would be, so it's, in this case it's 2 over my over 5, and then that's going to make it 2/5. That's going to make it 10/5.
10. Okay? M sub y would be 10. Okay? mx5, m sub y 10. Good for them. Okay? That was 3. Number 4. Explain how the symmetry principle is used to conclude that the centroid of a rectangle is the center of the rectangle.
Two symmetric axes.
What's that?
It's good. It's symmetric across 2 axes.
Yeah. Well, do you know what the... Okay, wait. Rectangle. For some reason I was thinking triangle. Yeah. So, this is number 4.
It's also could have a center of mass in the middle. It would be
Okay. So, explain how the symmetry principle is used to conclude that the centroid of a rectangle is the center of the rectangle. Well, if I understood you right, to find the center of a rectangle, you go your 2 diagonals, right?
right.
There's the center. Now, because each of those diagonals splits the rectangle exactly in 2, then the center of mass has to be on each of those lines, because that's what we learned back before the symmetry principle. If a lamina is symmetric with respect to a line, then the centroid lies on that line. Okay, and mine's not a very pretty rectangle, but if it was even and stuff, this would indicate, because that is the center of mass has to be on that rectangle, okay, on that line, and it has to be on this one. The only place they intersect is right in the center. So I think that's all you have to do for that one. Let me see if they do say anything else that might be clarifying. I can imagine that they could. Yeah. Because a rectangle is symmetric with respect to both the vertical line and the horizontal line through the center of the rectangle. Okay, they did it this way. And this probably is better, because that way, for sure, the center of mass has to be on either side of this, and also top to bottom, so this line and that line. So actually that's better than the diagonals, okay? Though it's going to be true of the diagonals as well, but it's the horizontal and vertical would actually be better. Okay. So same argument though. If the center of mass, if that is indeed bisects the rectangle, the vertical and the horizontal do, then if it's lamma, then the center of mass has to be on those 2 lines. The only place they intersect is at the center. Okay. Number 5. Give an example of a plate such that its center of mass does not occur at any point on the plate.
Plates are such that the center mass does not occur on the plate.
Yeah. Now don't think a plate that you would eat on.
Right. That would be like a steel plate with a hole punched through it.
Exactly. If you had a washer.
Yeah.
Okay, the center of mass is going to be in the center, but that's not on the plate.
Right.
Okay. That's the best I can think of. Let's see if they think of another one. If the plate looks like a ring, then the center of mass doesn't occur at any point on the plate. Same deal.
Right.
And then, number 6, draw a plate such that its center of mass occurs on its boundary You do not need to verify this fact. It should be believable from the drawing.
I guess I think that's kind of like a C channel.
Yes, exactly. Something like that. And I don't know if I drew it so it would be, but the center of mass, if you brought these in enough, the center of mass could be on that boundary. Probably have more distance. Yeah. Okay. Yeah, but that's exactly right. All right. Homework exercises 8.3. Any of the odds 1 through 9. Any of the odds 11 through 17. Do 19. Any of the odds 21 to 25. Any of do 27. And either 29 or 31 or both. Any of the odds 33 through either 33 or 35, either 37 or 39 or both. And then you could do 41 if you're interested. Okay? There's more on a median and symmetry principles if that's of interest to you. Now, Taylor polynomials, here's an English mathematician, Brooke Taylor, made important contributions to calculus and physics, as well as the theory of linear perspective used in drawing. Anyway, that's another potential paper topic, but I wish we had time to do these. These are fascinating things to study, but we just don't have enough time to do it. There is also, related to a Taylor polynomial, is the Maclaurin polynomial. And the bizarre thing to me is this Scottish mathematician Colin Maclaurin came well after Brooke Taylor, from England. Well, they were contemporaries for much of their lives, but he was younger. Professor Edinburgh. Newton was so impressed with his work that he once offered to pay part of Maclaurin's salary. So he must have been pretty impressive. But it seems like to me Maclaurin's is always a special case of Taylor's, but I don't know if Taylor just didn't recognize it or what. But anyway, there's two potential paper topics. The error bound for Taylor polynomials are given here, and it's just incredible how fast that can get very small very quickly. So, I'm not going to do any more on that. So we're going to skip chapter 9, that's differential equations. That's another course. You could write on anything in that chapter if you wanted to, but of course the book can't be your source. So let's move on to infinite series. Let's go and do that. All right. That. Move on to 10. All right. I have to go get more water because my head's drying out again. I'm going to try to proceed. Okay. Now, the old edition of the book had this fantastic, I think it's pretty, sure looks like a picture taken by the Hubble Space Telescope. It doesn't give that credit here.
Either going to be that or Kepler.
Right. And here, in your text is infinite series allows us to make sense of the process that iterates infinity as occurs within fractals, generating patterns such as this line. So, such as this one. I was going to say that's not a line, but anyway, it's just a lead-off thing. The old one said this. Our knowledge of what stars are made of is based on a study of the sources spectra, the sequences of wavelengths absorbed by gases in the star's atmosphere. So, again, it's a sequence. That's what they're getting at. And what do we mean by a sequence? Okay? Before we get to this slide, let's do a theory of it. Infinite series is a third branch of calculus. There's integral calculus, differential calculus, and infinite series calculus. Okay, infinite series provide a new perspective on functions and on many of the interesting numbers. And frankly, Taylor polynomials were infinite series. So why they didn't do that in this chapter, I don't know. But here is an interesting. I don't know if you've hit this before, but here is exactly, what e to the x is. One plus x squared over 2. I probably should say factorial, but that's just that, plus x3 over 3 factorial plus x fourth over 4 factorial plus ... It keeps on going forever. What's that?
Is the definition summed up as, oh, sorry, it's
Yeah.
Yes.
Do you have it?
So E is a Taylor series, basically.
Yeah. And that's how it's defined. So it's sine, so it's cosine. So many of our functions are basically Taylor series. They don't call them Taylor series here, but that's what they are. If you got a calculator, or is that, you got one on your computer there? Or you got a calculator?
I got 84, so I think it's probably good.
Yeah, okay. Just do e to the 1 and see what you get.
So it's a function e to the first, and we get 2.7182
Okay, something like that.
1828, so repeating decimals.
No, it's not. It looks like it will be, but it won't. It won't repeat forever.
Really?
Yeah. If it was repeating, it wouldn't be an irrational number. E is an irrational number.
Oh, that's right, because isn't it like e plus I is some definition?
That's Euler's formula. Is see if I can get it right. E to the I pi is equal to 1. I think that's it.
Right.
Yeah. Irrational all the way. Let's just see, if you got your calculator out, let's just do it. 1 plus 1, really high level math today. Okay. Plus 1/2
5
plus 1/6
plus
1/24.
4.
What are we up to now? What's that?
So far, okay, so we're at 2.708.
Okay, 2.7. So you're already basically pretty close to 3 significant digits.
Yep.
Let's do one more, plus 1 over 120.
Plus 1 over what, 120?
Yeah, that would be 5 factorial.
Okay, so now we're at 2.716.
Okay, you're almost to 4 significant digits, plus 1 over, what was the last one, 20?
1 over
120 times 6, whatever that is. That's 720.
I could put it in factorial, but so now we're at 2.71805 repeating.
Say that again.
2.71805 repeating.
Goodness gracious, you're almost at 1, 2, 3, 4, 5, 6 significant digits, plus 1 over 7 factorial.
So the factorial list. A lot of options.
Oh, okay, I thought you had a button on that.
Yeah, the TIA cord doesn't, which is
Yeah.
fine.
You gotta go to
And so you do 1 over, and then you go to statistics. Then what that math, I'm gonna get math, and then probability. Didn't expect this to take so long. It's a long function in the cursor. Not move very fast. Very good. Math, probability, factorial. So that is 2.71825.
2.718.
25.
Okay. We may have gotten off a little bit. Anyway, you see, we got there pretty closely,
Yeah.
pretty quickly.
So just a few iterations of the series.
Yeah. Yeah, and that's exactly what your calculator is doing when you tell it e to the 7 thirds or 7 pies or something. It's just shoot, doing several of these right after. The numbers there would be, each term would be a number of a sequence. When you add them together, that gives you a series, okay? Now, the Gregory-Leibniz series, okay, which would be this one, pi fourths, and if you'll punch that in and see what that is, it's something about 0.76 maybe. Yeah.
So we got 0.753.
Okay, a little, okay, 0.753 what?
Oh, 785.
Oh, 7853, okay.
853 981 634.
634? Okay, it keeps on going. Okay, let's see what its is. Okay, that would be 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13 minus 1/15 plus 1/17 minus 1/19. I could write plus 1/21. Okay, let's see how quickly we can get there. 1 minus 1/3. This will be sort of a pain to do, but
Yeah, exactly. Fraction every time. 1/3. We'll show you copy paste feature.
plus 1 plus 0.2. Many of them we could do that easily, but we could do that. 1/5, huh? 1/5 is 0.2. You could, that would be, all right, you did, okay. Minus 1/7 plus 1/9, and just keep sort of looking at the totals every time you do this.
So far, yeah, we're pretty close. 0.723.
Okay, keep going there. What was the last one?
1/7.
Plus 1/9. What's that one?
And then the next one is minus 1.
Yeah.
A lot of prime numbers in
Yeah.
this series. Okay, that puts at 0.744.
We're getting closer. What was that? The last one, minus 1/11?
Yeah.
Plus 1/13?
Puts at 0.82093.
Okay. Say that again.
0.82093.
Whoa, yeah, we messed up something there. It should still be in the 0.7 range.
I think it's because we go up.
Oh,
we're
up and down,
overshooting and we're
up and down.
undershooting. Yeah, so we're gonna
Okay.
keep going.
I thought we were past that, but
It's
okay.
like it's like a continuous sine wave. It'll just
Right,
keep going
yeah,
down.
a
converge
down
as
sine
it's-
wave, yeah. Okay, but you see, you will get there in time, and it's fairly quick too. So let's start, that's more series, but let's go back to a sequence. What is a sequence? A sequence of numbers appears in a variety of situations. You can divide a cake in half. Looks like more of a pie to me, but it doesn't. I guess they don't want to say pies. That might get people confused. But a cake in half, and this would be a whole cake, plus a half cake, plus a quarter cake, plus an eighth cake, plus a... Every time you divide it, you get another portion of the cake. What would be the next amount to this? 1, 1/2, 1/4, 1/8.
Are we doing by binary numbers?
Yeah, you're dividing by 2 every time.
Okay, so it would be 16, 32, 64, 128.
Exactly. So that would be a sequence of numbers. Notice we're not adding anything, we're just having the numbers, and each one is related to the previous one. So that one we could express as f of n, where n is how far we've gone, how many steps we've taken, would be 1 over 2 to the nth. Because if you look at this, this is 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, 1 over 2 to the 4. So yeah, each number is represented by that exactly. Okay? And this is for n 0, 1, 2, 3, ... Okay, keeps on going. Now, here's your definition. Whoa. Well, they got them out of order. Let's go and do the definition. No, the definition of a sequence. They don't do it anymore. They go right to a limit of a sequence. Before we do that then, let's do the definition of a sequence here. A sequence, A sub n, and that's how we refer to it too, embraces a sequence, A sub n, God, my eye itches, is an ordered collection of numbers defined by a function defined by some function f on a set of sequential integers. Okay? My head's hurting. The values A sub n now this A sub n is the nth member of that sequence, okay? And that would be that same function of n that we mentioned before, okay? Those are called the terms of the sequence. Terms of the sequence. Okay. The N is called the index. Okay? Informally, we think of the sequence I think I may have to go get some more water. My throat is so dry. N is called the, I didn't write that. N is called the index, I got that. Informally, we think of a sequence as a list of terms. So we can think of it as A sub 1, A sub 2, A sub 3, A sub 4. It's just a list of terms. And generally, we don't even put commas in between them. Yeah, they do, I guess. And the sequence does not have to start at n equal 1. It can start at n equals 0, n equal 2, or any other integer. Strangely enough, those should even be negative integers, which is really bizarre. I can't think of many cases I'd want to do that, but they could. Okay? One sequence that they use that you run into in physics is the Balmer series of absorption wavelengths of hydrogen atom in nanometers. Plays a key role in spectroscopy, and that's the last one we're going to list here. Oh, that's this one here, is the Balmer series. Okay. All right, so here are just a few of those. Now, I'll blow this up. I'm sorry. I've got to sneeze. Yuck! Makes my head hurt even worse. Okay. Now, here's how we refer to a series, okay? A sub n. Now, you can't start any old series anywhere because you can't use terms that are undefined, or don't exist. So this one, A sub n, is 1 minus 1 over n. Pretty obvious n cannot be 0 because you can't have 1 minus 1 over 0. You just can't do it. So this one you're going to have to start no earlier than 1. You could have n greater than or equal to 1. So this would be the series. Now, if n were equal to 1, that would be 1 minus 1 over 1, which is 1 minus 1 over 1.
That should be 1 or 0.
0.
Yeah.
1 minus 1 over 2.
1 half.
1 half. 1 over 1 minus 3. 1 over 3.
2/3.
2/3. 1 over 1. 1 minus 1 over 4 would be 3/4, and on like this. That's a sequence. This is one way to express it. Okay? Another way to express it would be n minus 1 over n. Right?
Yeah.
Okay? Because that would be 0 over 1, 1 over 2, 2 over 3, 2 over 4. To me, that's a little easier to see and write down. Here's another sequence. If you want to alternate signs, you do a -1 raised to the n, or n minus 1, or n plus 1. You can do it a variety of ways. But if that's it, and this one, if you are letting it start at 0, then that would be perfectly different. The first number in that series would be 0 because it would be a negative it would be a 1 times 0, it would be 0. And when you let n equal 1, negative 1 to the 1 is minus 1 times 1, that would be a minus 1. N equal 2, this would then become a positive 1 times 2 would be 2, negative 3 plus 4, minus 5 plus 6, minus 7, on. And then the third one here happens to be the Balmer series, okay? That n doesn't start until 3. It can't start before 3 because they do n squared minus 4 in the denominator, and so n cannot be 2. So it can start at 3 and anywhere on up. And it's a bizarre number, 364.5 raised to the times n squared divided by n squared minus 4. That's not a particularly easy one to calculate, but you can. Here is 1, 2, 3, 4, 5. That's up to the 5th term. Let's do to the 6th term. Let's do 3, 4, 5, 6, 7. So let's do 8. 364.5 times 8 squared will be 64. Over 64 minus 60. Minus 4 would be 60. And you can see what you would get. Okay, so you can keep tracking those. What you'll find, if you do enough of them, the limit of these, I think we'll see this later, is going to be 364.5. Now, we haven't talked about the limit yet. That will be, that's what they're getting closer and closer to, because n squared over n squared is 1. And I think that's what be the way that one ends. All right. Now, there's another term here that they bolded, and that is the general term for the sequence, and that's what we listed here at the beginning. But there's more than one way to write them sometimes. Okay, like that first one would be n minus 1 over n. That would be another way to write that general term. There is another type of sequence that is one that's defined recursively. In other words, it doesn't have a general term like, well, it may, but it's actually defined based on what the previous term was or were. Okay? This is a very famous one, and it's the Fibonacci series. And they don't seem to be going to show that here. So I think I'll do that next. I hate to break again, but my goodness, my head is hurting. Let me take just a couple minutes and go down and get something else. All right. So there's the example of a general term. We're going to do Fibonacci series. Let's clear this ink off. You're familiar with it? Okay. Do you know how it goes?
Some of the previous terms, the previous two terms.
Okay, it starts with 1, and
then it's 2,
okay, actually it's a 1 again, so you can add to be 2.
yeah, 2, and 3, 5. And so on 8, yeah, and 8, 5, which is
Okay,
8, which is 21, 13, 34, 3, which is 55.
and it keeps on trucking. Okay, now, I can't do a general term for that one, or there may be one, but I can't think of what it would be, because this one is defined recursively. Each term depends on what the previous term or terms were. This one, the previous 2 terms. So it's really hard to say the nth term is going to be this, because nth term depends on what the n minus 2 and the n minus 1 were. It's the sum of those 2. So that is Fibonacci series. Is that just a little freaky, weird type thing, or any practical application of this? There are dozens of things. Have you ever heard of the term called the golden mean, I believe it is? The golden ratio, golden ratio.
Yeah.
Golden ratio, that comes out of here. The Parthenon that the Greeks built in,
Right.
I don't know if it's in Athens or near Athens or something,
It's on Mount-
but
it's
the,
on mountains.
what's that?
I think it's on a mountain outside of that.
Right, and it's the dimensions of it follow that golden ratio, which follows Fibonacci series, which they probably didn't even know. I don't know, they may have by then. They show a picture in the book, sunflower, the spiral of the seeds in a sunflower, Fibonacci series, okay? The spiral of a certain of your seashells, their spiral, they follow Fibonacci series. I mean, so many things in nature. You remember Leonardo's Da Vinci picture of the man?
Oh, yeah, the outstretched arms.
And that's all based on the Fibonacci series, the golden ratio. There are just tons of different things that it just keeps popping up, and you wonder where in the world did it come from, okay? If we take the limit of the n plus first term divided by the nth term, we'll obtain a phi. So the n plus first term divided by n term, these are the okay, divide those out, and the limit of that is a number, the limit of this as n goes to infinity will be a number phi, which is 1 plus the square root of 5 over 2, which is approximately equal to 1.618. Okay? And that's called the golden mean. Okay, I was saying golden ratio, but it was golden mean. According to the ancient Greeks, that quantity gives the ideal ratio of the sides of a rectangle, and that's how they built the Parthenon. The face of the Parthenon was designed to reflect that ratio. Okay, so here is another recursively defined sequence. Compute A2, A3, and A4 for the sequence defined recursively by A1 is equal to 1. A sub n is equal to 1/2 times a to the n minus 1 plus 2 over a to the n minus 1. That's all you need to define a recursive sequence. You need a starting term and then the formula for the term that follows. Unless, of course, your term that follows depends on the previous two terms, then you'll need the first two terms and then the formula, because you got to have enough to do it. So you got a sub 1. Can you tell me what a sub 2 is? I think I'll move this. Can you tell me what a sub 2 is?
Oh, yeah, 2 over 1.
Right? That would be negative 1/2, right? Okay. How about a sub 3? Now wait a minute. It looks like to me it's got to be a minus, but they don't have a minus. Oh, it's because that's not a minus there. Okay. Yeah, okay, got it.
Okay. Wouldn't that be 1 plus 1/2? That would be 1. Wouldn't be 3/2. 3/2 times 1/2 would be how much? 5, 2.
No, goodness gracious, how am I messing it up so badly? All right. Okay, let's get back again. It'd be 1/2 times 1/2 plus 2 over 1/2. No, wait. I messed up too. That's where I messed up.
Yeah.
That's 3/2. Wait.
Yeah.
Let me back up some.
3/2. Yeah.
Wait. All right. That's why it wasn't coming out right, because I messed this one up. All right. Well, I messed it up because I had the minus sign in there. I didn't go back and check to see. So that'd be 3/2, yeah. Because it's 1 plus 2 is 3 over, yeah. Okay. And then a sub 3 would be 1/2 of 3/2 plus 2 over 3/2. And that would be 3/4 plus and 1/2, I think 2/3, isn't it?
Yeah, yes.
That would be 9 plus 6, 17. 17/12, yes, okay. A sub 4 would be 1/2 of 17/12 plus 2 over 17/12, which would be, yuck, 17 over 24 plus 2 Two over $17.6, I think, which would be 17/24 plus 12 over 17, which I don't even want to do that, but yeah, the denominators get really bad really quickly. So I'll take their word for it. 577 over 408. Okay, now, if you were to write these out as decimals, 1, 1.5, and then they give this next one as 1.4167. 1.4167, and this next one they give is 1.414216. Okay, I've got a really sneaking suspicion that's going to come out being the square root of 2. So that's getting awfully close to square root of 2 right there. Let's see if that is indeed the case. I was just guessing. Well, they don't say. It may not be. But it sure seemed like it was heading that way. Oh, wait, yeah. You may recognize the sequence in example 2 as a sequence of approximations to square root of 2, which is 1.41421636, blah, blah, blah. So you see we're already 1.414216. So we're awfully close after just a few times. Okay. All right. Our main goal is to study the convergence of sequences. That's what we're most interested in. And here's a clue or a sentence. A sequence A sub n converges to a limit L if A sub n minus L, the absolute value of that, becomes arbitrarily small when n is sufficiently large, okay? Becomes arbitrarily small when n is sufficiently large. A lot of weasel words in there. Here is the formal definition, and that is this one. Okay. All right. Yeah, I didn't know that. That's there. I think this is about all we're going to have time for. Limit of a sequence. We say that the sequence A sub n, and that's when you see the braces with a base and a subscript that's an integer, that is a sequence. We say that that sequence A sub n converges, and A sub n is the general term, converges to a limit L, and we write the limit as n approaches infinity of A sub n is equal to L, or you just say that A sub n approaches L, because you see, it's that last term is the one going to the limit. Later when we do series, that's a sum, so it's not necessarily, but this is just A sub n going to L. If for every epsilon greater than 0, this sounds familiar, good old limit nomenclature. For every epsilon greater than 0, there is a number capital M such that the absolute value of the A sub n minus L is less than epsilon, okay, for all n greater than that number M, okay? Means if you go out far enough, no matter how small you choose your epsilon to be, you can go out far enough so that you guarantee that if you go out far enough, this difference here will be less than epsilon for every n that you get greater than that. If no limit exists, we say that the sequence A sub n diverges, and if the terms increase without bound, we say that A sub n diverges to infinity. Okay? Now, to me, diverge says it all, but there are some that diverge that don't go to infinity, others that diverge to infinity. So we'll look at those two cases later. We will start next time. Well, we'll start on this slide here, which basically describes that definitional limit. I probably should have just paused a little earlier and done that with it. But we'll start at the top of this page here, page 515. Okay? Now, homework exercises here. We didn't get very many done, but let's see how far we can go. Okay? I think you can do number 1 and any of the odds 3 through 11. And I doubt if we've done enough for you to do 15 yet. Well, wait, 13. Try number 13. I don't know for sure if we'll do one just like that, but I think you can try that and see if you can come up with a formula for the nth term. And I don't think, have we done theorem 1 yet? I don't think so. No. So we'll hold off and just go through 13. All right, good deal. Sorry that I've had so many 2 interruptions today. Actually, more than that with the student. So all we're going to do is 10.1 and 10.2. We should finish both of those hopefully next time. And then on Monday, it looks like we may only get 11. I doubt if we'll get to 12. Okay? So